everyone. Hope you are safe and sound. This is the fourth part of solid state series. I hope you have followed the previous lectures of this series. If not, you will get the link of those lectures in the description. Please follow the lectures sequentially for better understanding. So in today's class, we will cover these topics that are packing efficiency, imperfections or defects in crystalline solids, and we will study types of point defects in details. So let's start. So our first topic is packing efficiency. Now we know that the constituent particles, be it be atoms, molecules or ions, they are closely packed in space, and this close packing is achieved either by CCP or by HCP, as we have seen in our last lecture. But in both these packings, there are some empty spaces or voids that are not occupied by the particles. That is, the total space is not occupied. So, the percentage of total space which is occupied by the particles in a packing is known as packing efficiency. And if we calculate it in terms of fraction, then the fraction of total space which is occupied by the particles is called the packing fraction. So here we shall calculate the packing efficiency for cubic unit cells, that is for simple cubic unit cell, face-centered cubic unit cell and body-centered cubic unit cell, and we shall consider that they have same types of atoms. Here are few notations, that is A is edge length of unit cell, R is radius of the sphere, and D is distance between centers of two nearest spheres, which is also called nearest neighbor distance, and D would be equal to sum of the radius of the two spheres, that is equal to 2r. So first we will calculate the packing efficiency for simple cubic unit cell. Now we know in simple cubic unit cell there is one atom per unit cell and 8 points are present at 8 corners of the unit cell, right? So this is the front view or view of one of the wall of the unit cell, and we know R is radius of the sphere and A is edge length of the unit cell. So edge length of the unit cell A is actually equal to sum of the radius of two spheres, that is equal to 2r, as we can see from here. Also D is equals to 2r, right? And we have seen edge length of unit cell A is equals to 2r, so we can write D is equals to A, right? Now if we calculate volume of the cube, which is actually equal to A cube, then it will be equal to 2r whole cube, that is 8r cube. Next is volume occupied by one sphere, which is equal to 4 by 3 pi r cube. Now if we calculate percentage of volume occupied, then it is given as volume of sphere by volume of cube into 100, which can be written as 4 by 3 pi r cube by 8 r cube into 100. So percentage of volume occupied is actually packing efficiency, and this value, if we calculate, we will obtain this, and on calculation of this value we will get packing efficiency as 52.4%, and in terms of fraction it will be equal to 0.524. So these are the values of packing efficiency and packing fraction for simple cubic unit cell. Now we will calculate packing efficiency of face-centered cubic unit cell. So in face-centered unit cell, we know there are 4 atoms per unit cell, and in the unit cell there will be 8 points at 8 corners and 6 points at center of 6 spaces. So this is the front view or view of one of the wall of face-centered cubic unit cell. R is radius of the sphere and A is edge length of the unit cell. So volume occupied by one sphere is given as 4 by 3 pi r cube. Now we have 4 atoms or 4 spheres. So volume occupied by 4 spheres will be equal to 4 into 4 by 3 pi r cube, that is equal to 16 by 3 pi r cube. Now let us consider triangle ABC, and if we apply Pythagoras theorem, AC square would be equal to AB square plus BC square. So here I have shown triangle ABC separately. So from this figure we can say AC is equal to 4R, right? AB and BC are edge length of the unit cell, so they will be equal to A. Now if I put these values in this equation, we will get 16R square is equals to A square plus A square, or 16R square is equals to 2A square, or A is equal to root under 8R square. So we will get the value of A as root under 8R. Now if we write this in terms of radius R, so it will be R is equals to A by root 8, which will be equal to A by 2 root 2. Now we know D is equals to 2R. That will be 2 into A by 2 root 2, and thus we will get D is equals to A by root 2. Next is volume of cube, which is given by A cube. So that will be equal to root under 8R whole cube. So we will get volume of cube is equals to 8 root 8R cube. Now if we calculate percentage of volume occupied, which is given as volume of sphere by volume of cube into 100. So we will get 16 by 3 pi r cube by 8 root 8 r cube into 100. Percentage of volume occupied is actually packing efficiency, and if we calculate this, we will obtain this, and on calculation of these values, we will get packing efficiency as 74%. And if we write it in terms of fraction, it will be equal to 0.74. So for face-centered cubic unit cell, these are the values of packing efficiency and packing fraction. So last we have body-centered cubic unit cell. So for body-centered cubic unit cell, we know there are 2 atoms per unit cell, and in the unit cell, there are 8 points at 8 corners of the unit cell and 1 point at the center or body of the unit cell. This is another representation of body-centered cubic unit cell. So you can see this 8 points are at 8 corners, and this point is actually present at the center of the unit cell. So A is edge length of the unit cell and R is radius of the sphere. Now volume occupied by one sphere is given as 4 by 3 pi r cube. We have 2 atoms or 2 spheres. So volume occupied by 2 spheres will be equal to 2 into 4 by 3 pi r cube, that is equal to 8 by 3 pi r cube. Now let us consider triangle ABC and BCD. So here I have shown triangle ABC and BCD separately. Now if we apply Pythagoras theorem for triangle ABC, we can write AB square is equals to BC square plus AC square. Now again if we apply Pythagoras theorem for triangle BCD, we can write BC square is equals to CD square plus BD square. So we can put the value of BC square in this equation, right? So we will put this value of BC square in this equation, and we will get AB square is equals to CD square plus BD square plus AC square, right? Now AC, CD and BD are the edges of the unit cell. So they will be equal to edge length of the unit cell, that is A. And as we can see from this figure, AB is equals to 4R, right? Now if we put these values in this equation, we will get 16R square is equals to A square plus A square plus A square, or 16R square is equals to 3A square, or A is equals to root under 16r squared by 3. So we will get edge length A is equals to 4r by root 3. Now if we write this in terms of radius r, we can write r is equals to root 3a by 4. Right? Now we know d is equals to 2r. That is 2 into root 3a by 4. So we will get d is equals to root 3a by 2. Next is volume of cube, which is given as a cube. That will be equal to 4r by root 3 whole cube. So volume of cube will be equal to 64 by 3 root 3r cube. Now if we calculate percentage of volume occupied, which is given as volume of sphere by volume of cube into 100, we will get 8 by 3 pi r cube by 64 by 3 root 3r cube into 100. So percentage of volume occupied is packing efficiency, and on calculation of this we will obtain this, and if we calculate these values we will get packing efficiency as 68%, and in terms of fraction it can be written as 0.68. So for body centered cubic unit cell, these are the values of packing efficiency and packing fraction, right? Our next topic is imperfections or defects in crystalline solids. So it is almost impossible to obtain an ideal crystal because they suffer from certain defects. These defects are called imperfections. These defects are actually irregularities in arrangement of the constituent particles in the space lattice, and they are also called as crystal defects. So crystal defects are of two types. The first type is point or atomic defects. So what are point or atomic defects? So if the irregularities or the deviations occur around a point or an atom in a crystalline solid, then they will be called point or atomic defects. The other type of crystal defect is line defects. So what are line defects? If the irregularities or deviation occur in entire rows of lattice points, then they will be called line defects. Now for the syllabus of 12th JEE and NEET, only point defect is included. So we will read only point defect in details. So point defects are further classified into three types. They are stoichiometric defects, non-stoichiometric defects, and impurity defects. We will read about these defects in the following slide in details. First, we will study about stoichiometric defect. So stoichiometric defect is also known as intrinsic defect or thermodynamic defect. So in stoichiometric defect, the stoichiometry of the solid will not be disturbed. That is, the constituents will be present in the same ratio as predicted by their formula in stoichiometric defect. So stoichiometric defects are of four types. So the first type is vacancy defect. Now in vacancy defect, some lattice sites will be vacant. So this is a perfect crystalline solid, right? Now if an atom or a particle is missing from the lattice site, then it will give rise to vacancy defect. So the lattice site which is now vacant are actually called vacancies. Now vacancy defect is created upon heating, and since some atoms are missing from the lattice site, the overall density of the solid will decrease, right? The next type of stoichiometric defect is interstitial defect. Now in interstitial defect, some constituent particles will occupy interstitial sites. So again, this is a perfect crystalline solid, right? And these are interstitial sites or voids, correct? Now if some constituent particle or atoms are present in the interstitial sites, then it will give rise to interstitial defect. And these atoms or points which are present in the interstitial sites are called interstitials. Now, as some extra atoms are present in the solid, the overall density of the solid will increase, right? So, both the vacancy defect and interstitial defect are shown by non-ionic solids. For ionic solids, they suffer from Schottky defect and Frenkel defect. And in both Schottky and Frenkel defect, the electrical neutrality will be maintained. So, the third type of stoichiometric defect which is shown by ionic solid is Schottky defect. So, in Schottky defect, equal number of cations and anions will be missing from lattice side. So, this is a perfect crystalline ionic solid. Now, if one cation and one anion is missing from lattice side, that is equal number of cation and anion are missing from lattice side, it will give rise to Schottky defect. And since equal number of cations and anions are missing, the electrical neutrality of the solid is maintained. Vacancies or holes are created at the positions from where the ions are missing. So, the position from where cation will be missing is called cation vacancy, and the position from where anion is missing is called the anion vacancy. Now, what are the conditions that will favor Schottky defect? So, ionic compounds with high coordination number will suffer from Schottky defect, and ionic compounds where cations and anions have identical sizes will also suffer from Schottky defect. Coming to examples. So, alkali metal halides such as NaCl, KCl shows Schottky defect. Now, in NaCl or KCl, the size of cation, that is Na plus and Cl minus, are almost same, right? So, also for KCl, size of K plus and Cl minus are almost same. So, they suffer from Schottky defect. Coming to consequences of Schottky defect. Now, since some ions are missing from lattice sites, the density of the solid will decrease, right? Due to presence of holes, the stability of the crystal will decrease and lattice energy will also be decreased, right? Electrical conductivity of the solid will increase because of the movement of the holes. Now, because some holes are generated, adjacent ions can move to these holes. As a result, new holes will be generated at other positions, right? And as a result, due to the movement of the ions or due to the movement of the holes, the electrical conductivity of the overall solid will increase, right? So, the fourth type of stoichiometric defect which is shown by ionic solid is Frenkel defect. So, in Frenkel defect, some ions, generally the cations, leave their normal lattice sites and occupy interstitial sites. So, this is an example of perfect crystalline ionic solid. Now, this cation can leave its normal lattice site and occupy any of the empty spaces or interstitial sites anywhere in this crystal lattice, like this. So, this cation is not present in its own lattice site but is present at some interstitial site, thus giving rise to Frenkel defect. Since no ions are missing from the crystal lattice, but this cation is present at some other site and not in its own lattice site, the overall electrical neutrality is same, right? So, the position from where cation is missing is called cation vacancy, and this is the cation at the interstitial site. Now, coming to conditions favoring Frenkel defect. So, ionic compounds with low coordination number shows Frenkel defect, and ionic compounds where anions are bigger than cations will show Frenkel defect. So, cations, because of the small size, can easily leave the lattice site and occupy interstitial sites, right? That's why I've said generally the cations leave their lattice sites and not the anions. Coming to examples. AgCl ZnS shows Frenkel defect. In AgCl, size of Ag plus is much smaller than size of Cl minus. So Ag plus can easily leave the lattice site and occupy interstitial site. So also for ZnS, size of Zn2 plus is much smaller than size of S2 minus. So it will also show Frenkel defect. Next is consequences of Frenkel defect. Now as I have said that ions are not missing from the crystal lattice, it is just that the cation has left its own lattice site and is present at some other position. The actual number of ions per unit volume is same, right? So density will also be same. But some holes has been generated. So due to the presence of holes, the stability of the crystal will decrease. Electrical conductivity of the solid will increase because ions are present at interstitial sites which can move at other interstitial positions as well. So due to the movement of ions, electrical conductivity will increase. So also holes are present. So again the holes can also move, and because of the movement of holes, the electrical conductivity will increase. Dielectric constant increases because similarly charged ions, here the cations have come closer. So dielectric constant value will increase, right? So the second type of point defect is non-stoichiometric defects. Now in non-stoichiometric defects, the stoichiometry is not maintained. So non-stoichiometric defects are of two types. One is metal excess defects and the other is metal deficiency defects. So first we will study about metal excess defects. So in metal excess defects, metal ions or positive ions are in excess, and this defect can arise in two ways, that is either by anion vacancies or by presence of extra cations at interstitial sites. So let's find out how metal excess defect arises by anion vacancies. So in this type of defect, anions are missing from lattice sites. So this is a perfect ionic crystal. Now suppose one anion is missing from the lattice site. So this lattice site is now left vacant. So electrons can occupy those holes so as to maintain electrical neutrality. As you can see, an electron comes and sits in the vacant lattice site, and now the overall electrical neutrality of the crystal is maintained. The anionic sites occupied by the electrons are called F centers. F means Farben-Center in German, which actually means color. So these centers, which are called F centers, are actually color centers because they are responsible for color of the compound. Examples are NaCl, KCl and other alkali halides. So let us consider a NaCl crystal. Now if we heat NaCl crystal in presence of sodium vapors. So on heating in presence of sodium vapors, on the surface of NaCl crystal, some sodium atoms will get diffused. So you can see some sodium atoms are diffused on the surface of NaCl crystal, right? Now if one Cl minus leaves the lattice site and gets diffused into the surface like this, then you can see this lattice site is now vacant. Now sodium atom will tend to combine with Cl minus, but in order to combine with Cl minus, this sodium atom must get ionized to Na plus, right? And in this ionization process, sodium atom must leave one electron, right? Now on ionization to Na plus, it can combine with Cl minus. So the electron generated during the ionization can now occupy the vacant lattice site, right? So this electron will be responsible for color of the NaCl crystal and it imparts yellow color to NaCl crystal. Similarly for KCl, when KCl is heated in presence of potassium vapors, the electron impart violet color to the crystal. Okay, so as you can see, now the ratio of Na plus and Cl minus ions are not same. That is, they are not 1:1. They are now 1:1 minus X because one Cl minus is missing from the crystal, right? So Cl minus are in less ratio. That is, the ratio is not 1:1 but 1:1 minus X. So we can say the positive ion or the metal ion is in excess. That is why it is a metal excess defect. And as you can see, the stoichiometry, that is 1:1, is not maintained. So this is a non-stoichiometric type of defect, right? Now let us find out how metal excess defect arises by presence of extra cations at interstitial sites. So in this type of defect, extra cations occupy interstitial sites. So this is a perfect ionic crystal. If one cation occupies one interstitial site, then electrons must occupy other interstitial sites to maintain electrical neutrality. So for one cation occupying the interstitial site, there must be one electron at other interstitial site, and now the overall electrical neutrality of the crystal is maintained, right? Coming to examples. So crystals suffering from Frenkel defect also suffers from this type of defect, such as ZNO. So ZNO is white when cold and yellow when hot. So let us consider ZNO crystal. So here the orange color positive ions are Zn2 plus and the blue color negative ions are O2 minus. Now on heating, what happens? On heating, ZNO generates Zn2 plus, half O2 and 2 electrons. Now suppose one Zn2 plus occupy one interstitial site. Then to balance the plus 2 charge of one Zn2 plus, 2 electrons must occupy other interstitial sites. Then only the overall electrical neutrality will be maintained, right? So let this be one Zn2 plus ion and this are the 2 electrons. So suppose this Zn2 plus ion occupies one interstitial site. So to balance this one Zn2 plus, there must be 2 electrons occupying other interstitial sites. So the overall electrical neutrality of the crystal is now maintained. Now coming to stoichiometry. So as you can see, the stoichiometry of Zn2 plus and O2 minus is not 1:1 anymore. Rather, because one Zn2 plus is extra in this crystal lattice occupying one interstitial site, the ratio is now 1 plus X:1. Correct. And as you can see, one Zn2 plus is in excess. That means metal ion is in excess. So we can say this is a metal excess defect. Also, the stoichiometry is not 1:1. So this type of defect is non-stoichiometric type of defect. Correct. These electrons are actually F centers and they will be responsible for color of the crystal. And this F centers imparts yellow color to ZNO on heating. Right. Next is consequences of metal excess defects. So, crystals suffering from metal excess defects are conducting in nature due to presence of electrons. However, conductivity will be low because the number of defects are small. They act as semiconductor known as N-type semiconductors because here the current is carried by movement of electrons. Also, the crystals will be paramagnetic because of presence of free electrons. These crystals are generally colored because of the presence of F centers. right? Now coming to the second type of non-stoichiometric defect, that is metal deficiency defects. So in metal deficiency defects, metal ion or positive ions are less as compared to anions. Now metal deficiency defects arises in two ways, either by cation vacancies or by presence of extra anions at interstitial sites. Now let us find out how metal deficiency defects arise by cation vacancies. So in this type of defect, cations are missing from lattice sites. So here I have considered a perfect ionic crystal. So the metal ions here are carrying +1 charge and the anions are carrying -1 charge. So suppose two metal ions are missing from lattice site. So since two metal ions of +1 charge are missing from lattice site, there is a deficiency of +2 charge in the lattice. Now this deficiency can be compensated by neighboring cations if they carry extra charge and occupy the lattice site. So suppose if the same metal carries extra valency of +2 and occupies one lattice site, then the deficiency of charge will now be compensated and thus we can say electrical neutrality is maintained. So because of this, some sites will remain vacant. So you can see one lattice site is vacant and thus a cation vacancy is generated. Coming to example. So this type of defect is shown by transition metals which are capable of showing variable oxidation state such as FeO. Now we know iron can exhibit both +2 and +3 valence states. So here I have shown a FeO crystal. So the orange colored ions are Fe2+ and the blue colored ions are O2-. Now suppose if 3 Fe2+ are missing from the crystal like this. So if 3 Fe2+ are missing, then there is a deficiency of +6 charge. So to maintain electrical neutrality, 2 Fe3+ have to occupy the lattice sites. Then only the +6 charge will be balanced. So here I have denoted Fe3+ by the red color ions. So as you can see, 2 Fe3+ occupies the vacant lattice sites and now the charge is compensated and electrical neutrality is maintained. So because of this, some vacant site is generated, that is the cation vacancy. Coming to stoichiometry. So since some metal ion is missing from the lattice site, the ratio is not 1:1, rather the ratio is 1 - x:1. And because some metal ion are missing, we can say this is a metal deficiency defect. And since the stoichiometry is not 1:1, it is a non-stoichiometric type of defect, right? Now let us find out how metal deficiency defects arise by presence of extra anions at interstitial sites. So this type of defect will arise if extra anions are present in interstitial sites. So again I have considered a perfect ionic crystal. Metal ions are carrying +1 charge and anions are carrying -1 charge. Now let us consider an anion with -1 charge occupying an interstitial site. So electrical neutrality can be maintained by neighboring cations which are in higher oxidation state than normal cations. So the extra -1 charge because of this anion can be balanced by an adjacent metal ion carrying +1 charge if it is replaced by same metal ion with higher valency of +2. Then the charge will be compensated and thus electrical neutrality will be maintained, right? But this type of defects are not very common because anions have larger sizes, thus they are not well accommodated in the interstitial sites. So this type of defect are not seen in crystals. Now coming to consequences of metal deficiency defects. So crystals suffering from metal deficiency defects also act as semiconductors. Now we have seen that in metal deficiency defects arising by cation vacancies, there are some holes. Conductivity is due to these holes, and so they are also known as p-type semiconductors. Now we shall read about the last type of point defect, that is impurity defect. By far the point defects that we have read do not have any foreign atoms. Now if some foreign atoms are present at lattice sites or interstitial sites in place of host atoms, it will give rise to impurity defects. So here I have shown a crystal lattice. As you can see, the blue color ions and the red colored ions are the normal host atoms of this crystal lattice. But you can also see a orange color foreign atom in this crystal lattice occupying one lattice side instead of normal red colored host atoms, thus giving rise to impurity defects. So this is achieved by adding impurity of other metal ions, and if the impurity are in different valence state, then vacancies will be created. So let us try to understand this by the help of an example. So suppose if a small amount of molten strontium chloride is mixed with molten NaCl and then they are cooled. So here I have shown NaCl crystal and this is strontium 2 plus from strontium chloride. So strontium 2 plus is the impurity of other metal ion. So here Na plus will get replaced by strontium 2 plus. Now if 2 Na plus leave their lattice side, then there will be a deficiency of plus 2 charge. So to compensate the plus 2 charge, one strontium 2 plus must occupy one lattice side, then only the electrical neutrality will be maintained like this. As a result, one lattice side will remain vacant. So we can see a cation vacancy is generated. So these vacancies increase the electrical conductance of the crystal. So with this, we have come to the end of our today's lecture. These are the topics which we will cover in our next lecture. You will get the PDF link of today's class in description. So if you have liked the video, don't forget to like, share and subscribe to the channel. Thank you.